This is Mr. Craig, and I'm going to go over a couple examples of what I'm looking for and what the AP exam is looking for when drawing Lewis structures and answering some of the questions that pertain to the previous video that I made here. The first example that I want to do is OCS, and it's the one that's at the bottom of your example sheet. The first thing we want to do is draw the correct Lewis structure, and I think we'll go in the order that we had on the sheet here. Determine the correct number of valence electrons. Well, we know that oxygen is in group 6A, so it's going to have 6 electrons. Carbon is in group 4A, so it has 4 electrons. And the sulfur is in group 6A as well, so it'll have 6 electrons for a grand total of 16 electrons. So we know that there's going to be 16 electrons in this structure. The next thing that we need to look at is determine which is the central atom. Well, we have carbon. Carbon's going in the middle. Arrange the atoms around the central atom and place the electrons around the external atoms first, keeping in mind the formal charges, and then place the remaining electrons on the central atom. So what we want to do is we want to have oxygen, carbon, and sulfur. And since oxygen and sulfur are in group 6A, we want to give those double bonds. We know that because that's the type of bond that these elements want as external atoms. Again, remember when we talked about group 6A, how they want double bonds. Group 6A wants double bonds, 7A wants a single bond, and group 5A wishes to have a triple bond as external atoms. Okay. Alright, now, so we have our elements, and again, we want to make sure that our external atoms get their electrons first. Now I'm just kind of scribbling on those electrons. So right now I have 2, 4, 6, 8, 10, 12, 14, 16 electrons. I have all the electrons that this compound needs. So there's no more electrons, or no other electrons will be placed on the carbon or the central atom. So this is our structure. And if we do the formal charge calculations, let's go ahead and do a formal charge calculation here just to prove that oxygen's happy. That we take the number of assigned electrons, which is equal to the number of lone electrons, 4, plus 1/2 of the shared number of electrons, which in this case is 2, 4. So that gives a total of 6 assigned electrons. The formal charge calculation would be the number of valence electrons, which is 6 for oxygen, it's in group 6A, minus the number of assigned. And if we do that, we have 0. Oxygen is very, very happy. Okay. Also, the same applies for sulfur, since it is also in group 6. So both the oxygen and sulfur want to have a double bond. The carbon, let's double check its formal charges. Number of lone electrons, carbon has 0. All the electrons it has are being shared, plus 1/2 of the number of shared electrons, which in this case is 2, 4, 6, 8. So the number of assigned electrons for carbon is 4. So the formal charge for carbon would be 4 valence electrons, because it's in group 4A, minus the 4 assigned electrons. So we have a 0 formal charge for the carbon as well. Okay, so everybody has a formal charge of 0, and that's what we want in this case. Now, I will say this right up front, that not all Lewis structures have the same charge or formal charge as it does charge on the compound. However, if we can get it to be at a formal charge of 0, or whatever the charge is on the compound, we want to strive to do that. Keeping in mind that we want our central atom to have a formal charge of 0. Okay. Alright, so we have our correct Lewis structure. Now the next thing would be nice if I could click on it, is the Vesper shape. Well, we have from our chart, okay, again we have 2 external atoms plus no lone pairs of electrons. Again, from our sheet here, our chart here, that the potential for this structure is 2, and potential again is defined as the number of external atoms plus lone pairs on the central atom. And since it has 2 external atoms and no lone pair, we have a linear shape. So this is a linear compound. Okay. The type of hybridization. Since it is a linear compound and there's two external atoms, the potential is 2. We should have 2 letters in our hybridization, S and P. So we have sp hybridization. Sigma and pi bonds. In this structure we have a sigma and a pi because that represents a double bond, but we have 2 sigma bonds and 2 pi bonds. So for this compound we have 2 sigma and 2 pi bonds. Okay. All right. Next question. It wants to know, indicate whether the compound is polar or not. Based on the previous video, I stated that if the external atoms are the same and there's no lone pairs on the central atom, it's a nonpolar compound. We do not have the same external atoms on this compound. Since we have different external atoms and we only have one central atom, this is a polar compound. Polar compound. Okay. All right, the next question. It wants to know the type of intramolecular forces. So intramolecular forces are the forces between atoms. So what kind of force do we have right between the oxygen and carbon? Well, they do not have the same electronegative value. Actually, oxygen has a much higher electronegative value than carbon. So this is a polar covalent bond. Same thing applies here between the carbon and the sulfur. We have 2 nonmetals that are sharing electrons, but they're not sharing them equally. So the intramolecular forces for this compound are polar covalent, and if asked again, polar covalent. Okay. All right, clean that up a little. All right, the next question is, what type of intermolecular forces do we have? Since this is a polar compound, we have the choices are ionic, dipole-dipole, and hydrogen bonding. So, number 1, there's no hydrogen. Number 2, there's no metal. So the only choice we have is dipole-dipole. Okay? So dipole-dipole bonds are our intermolecular forces. And the last thing that may be asked is the type of solid. So not a metallic solid, not an ionic solid, so down to molecular and network solid. Since we have 3 different kinds of atoms, that's at least 2 different types, this is a molecular solid. Okay. And let me stop right here.